Good day, everyone. I'm Roy Richardson, Vice President of Business Development for CellPlan Technologies. Welcome to the CellPlan webinar on spectrum analysis for LTE systems. The presenter today is Mr. Leonard Korowaichuk, and he will give a more detailed introduction of himself once I turn the floor over to him. Just a few logistics to go over before we start the session. During the webinar, all attendees will be in listen-only mode. If you have any questions during the webinar, you will see on your panel that there is a hand icon that you can actually raise to ask a question. We will take a break during the presentation to answer questions. We may not be able to get to all questions during the presentation, and those that we're not able to get to, we will at least answer via email. So please do send in your questions via the question box on the panel. Depending on your internet connection, you may encounter screen refresh issues from time to time. If that does occur, please click on the button that toggles from full screen to window and back to force an update of the screen. There is also a chat window where you can ping us if you encounter any issues during the webinar. With that said, and with all logistics from my side out of the way, I will now turn the session over to Leonard. Leonard?
Thank you, Roy. Thank you. Good morning, good afternoon, good evening. We have an international audience all over the world. It's a pleasure to be here again in this webinar. And today we will talk about spectrum analysis for LTE systems. So let me switch off my webcam so you don't need to look at me. Okay. Basically, my name is Leonard Korowaichuk. I am CEO and CTO with CellPlan International. Have been in telecom for more than 45 years. And have several patents and so on. Always work in R&D, manufacturing, and service areas. I have several books published. Designing CDMA 2000 systems has a large part about wireless design, so you may benefit here is this book. And then we have another book about LTE WiMAX and WLAN, Network Design Optimization Performance, both books published by Wiley. We are now writing the second edition of the LTE book. It will be 1,000 plus pages, a lot of material, new material has been added. And I hope to finish it by the end of this year. Then we have network video, that is another book that we are writing, mainly for applications for private and public safety. We are also writing a book about backhaul network design, multi-technologies, and all those already have contracts with Wiley, and we are now preparing a smart grid networks design also. A little bit of our company, CellPlan International. We are headquarters here in the USA. Actually, we have more than 500 employees already, 20 years in business, subsidiaries in 6 countries, but we operate worldwide. We are vendor independent, so we are really, it's an employee-owned company, so we really don't have any connection to any vendor and so on. Our flagship is our network design software, CellPlanner Suite, and now CellDesigner. We do a lot of network design services, network optimization, and network performance evaluation. All the continents and small, large, extremely large networks. We provide services to equipment vendors, operators, and consulting companies, and so on. We also do a lot of high-level consulting, so people, when they have difficult problems, they come to us. We do RFP preparation, we interface with vendors, between operators and vendors. We do technical audits, business plan preparation, and a lot of specialized stuff that requires really a deep knowledge of the technologies of RF and so on. We do some network managed services, and we support all technologies. We are complete technology agnostic. multi-technology, multi-band networks, backhaul, small cells, indoor head nets, and Wi-Fi offloading. This has been a very successful webinar series. We are in our 6th webinar, and you can see here a list of all our webinars. We have another one coming still this year. And feel free to send your suggestions for next year if you want some topics to be covered and so on. The first webinar was in May, How to Dimension User Traffic in 4G Networks. Is a webinar that we had participants from 44 countries on our live presentation, and we had 1 hour and all related to traffic, and really something that people are very, very interested, and you will see more in the books and also on the classes that we give. Of course, in the webinar, it's very limited how much we can present because of the time constraint, but we have much more content than the one present in the webinars. Webinar 2 was how to consider overhead in LTE dimensioning and what is the impact. 49 countries, already for 545 views. Also was a very popular webinar. We analyzed in depth the overhead in LTE. We gave an LTE refresher, and we discussed dimensioning and planning, and we presented a capacity calculator. It was a very interesting webinar, one of my favorites. Webinar 3 was in July. We have one per month, where we spoke about how to consider customer experience. We had participants from 40 countries and 404 YouTube views. And we basically spoke about how to consider customer experience, what factors are involved, what parameters, and how SINR availability can impact customer experience. Webinar 4 was about LTE measurements, what they mean and how they are used, 44 countries, 529 views. And it was quite an extensive webinar because we spoke about network measurements and field measurements, so it was a lot of information in this webinar. Webinar 5 was really extensive. We had to break it in 2 parts. Basically, we spoke about what LTE parameters need to be dimensioned and optimized. We spoke, first part was about the downlink, very, very popular, 69 countries, and it was less than 1 month ago, and we had 922 views. Actually, I think it's even more today. So it's a very, very popular webinar. This was part 1. Part 2 is the uplink. It was 15 days ago. We already have 208 views. So today we will have webinar number 6, spectrum analysis for LTE systems. I hope you will enjoy it very much. These are the topics of this webinar. Very extensive. It will be not so long. Today I believe we'll be able to do it with under 2 hours. But there is a lot of new things that you probably will not see anywhere else. The way we are looking in spectrum and we're analyzing spectrum. The next webinar, webinars number 7, will be MIMO. What is real and what is wishful thinking? It will be on November 5th. Please register, as we are already running out of space for this webinar. We have a hard limitation of 500 participants, so don't forget to register soon, early. And that's here are the topics that we will discuss in this webinar. Very, very interesting, very in-depth, and there is a lot of buzz about MIMO, people spending a lot of money, And the question is it worth it? What are the real benefits of it? I would like to call attention, we will have a technology network design and optimization bootcamp. This is a live class that we will give on December 8 to 12, is a whole week, and it will be at the University of West Indies in South Augustine in Trinidad. We already have more than half of the space occupied, so if you plan to participate, please register soon. It's not a free webinar, it's not a free class, but for a whole week you really will go very, very deep into the LTE technologies and all the information that you need. It basically has all the 7 webinars plus many other things included in this class. Some of the topics that will be covered are shown here, and we have a module A that is a LTE technology, and then we have a module B that is LTE network design. That really we don't have a webinar. We probably will have a webinar about LTE network design next year, but you know, in 2 hours, that's we have to limit what we can present, and we can also interact much less with the audience. Well, today's webinar, today's feature presentation, as they say in the movies, is the spectrum analysis for LTE system. We put a lot of effort in the preparation of this webinar, and you will see that you will get a lot of information. I would like to tell you a little bit about the topics that we will be presenting today. RF parameter characterization, spectrum analysis, channel technology analysis, CellSpectrum parameters, 3D, 2D, and 1D parameters. And then we will show a calibration of propagation models, comparing prediction and measurement, generating precision from measurement, and finally a summary. The list of 3D parameters that we will present are here, 2D parameters and 1D parameters. To illustrate all those topics, we will be using one of our products that we developed called CellSpectrum. Because it's very hard to talk about spectrum without showing, you know, pictures and things like this. So we decided to use CellSpectrum to illustrate. So I would like to tell you a little bit about RF parameter characterization in broadband channels and how CellSpectrum came to life. Basically, you know, when we work with narrowband channels like GSM, well, we had to consider that the behavior was uniform over the frequency band, but it will be having variations over time. Even so, it was already hard to calculate, you know, what was the fading. There was not really a way of measuring it. So we have to do educated guesses. But for GSM, that was fine. When CDMA came, the channels became broader. And we start noticing that, you know, with 1.25 megahertz, there was already some issues with parameters fading in frequency, fading in time, and issues with multipath propagation and so on. So basically, broadband channels present a significant variation in frequency and in time. And when we went to UMTS, this became evident. You know, 5 megahertz channels, and we never felt, I at least never felt comfortable having to guess the numbers and so on. And mainly when OFDM came with Wi-Fi technologies and so on, it became very difficult to characterize the entire network. And we have designs that we do that require very large reliability, like power plant automation based on wireless, and so on. And we need to provide, 4 or 5 nines of automation on a point-to-multipoint design, of reliability on a point-to-multipoint design. And then, because we couldn't really measure those variations, we have to be overprotective and leave a lot of juice on the table. So we decided that now, if there is nothing in the market that we can really use to characterize properly those channels, why don't we develop an equipment? So first we said, okay, what are the requirements for a broadband field spectrum and technology analyzer? In the industry, we had scanners and we had technology protocol decoders. The last ones based mainly on regular phones with a special software load on it and so on. But the parameters that they gave were basically one-dimensional parameters like power, noise, or cell IDs, and they will not really give us a full understanding of the behavior of the whole spectrum, what was the multipath, what was the fadings, and so on. And also the way they showed those 1D parameters were not really good enough for us to take decisions on the design and to find where the issues were happening. So there were several crucial parameters that we required, and they were not available because it required 2 and 3D dimensional analysis. So we said, okay, if there are nothing available in the market, can we do something in design? And that's what happened, and we started developing a product for our internal use. Basically, we started with the specs. First, we said, okay, we should capture the spectrum, not just measurements, because many times, we go to the field, we do measurements, and then, well, what about that other aspects that we didn't look? And everything was gone. So we said, okay, we need to develop something that really captures and stores the spectrum so we can go back and analyze something that we missed in the first drive test. We can go deeper, or we can, very shallow, because we start analyzing, we find that we don't need to go as deep as we thought we had, and so on. So basically we said, well, we must be able to analyze the spectrum in 3 dimensions. And we need to answer basically these questions here. What is the multipath delay spread everywhere in the network? We know that this varies with the locations in the network, but we had to know what was the real multipath delay spread. This is an essential parameter for OFDM. What is the expected time and frequency fading? Fading will imply in the amount of margins that we have to give to our design for a certain reliability. So it's an essential parameter. It varies with location. We had the test equipment that we can measure in one location or another location, but it really would not allow us to drive test and so on. Then MIMO came, and a question that everybody was asking us: how do I see the correlation between antennas? What is the average path loss? Well, we had to do a lot of CW measurements and so on. Can we integrate everything into one single product? How are the best servers distributed along the network? Well, this is provided by regular scanners, but the way it is provided was not really very smart. So we said, well, we need to have something more flexible. And mainly, how is traffic distributed in the LTE frame? Because LTE scheduling is something that is really not transparent to the user. So we said, well, it's very important that we analyze how the scheduler works. So, and that's all of this prompted then the design of our equipment called CellSpectrum. We will use CellSpectrum here. I'm not trying to promote it. It was developed as an internal tool. Several customers are requesting it, so we are selling units, but it was really developed for our internal use. It's an RF spectrum and channel analyzer. It's totally software-defined receiver. So by being a software-defined receiver, it is really independent of the technology, and it enables capturing, digitizing, storing, and analyzing the RF spectrum, and then we can analyze any technology. At this moment, we are doing LTE FDD, but our plans are to extend this to other technologies. The good thing is that it digitizes and stores up to 100 megahertz of spectrum at one time. So you can have a lot of information there. And also, it works from 100 megahertz to 18 gigahertz. Of course, we have units that go only up to 6 gigahertz, 8 gigahertz, and so on. But if needed, we could go up to 18 gigahertz. And it extracts parameters like the LTE channel response per resource element. That's very unique. There is nothing in the market that's capable of giving this. It calculates the multipath delay spread, the average frequency fading, average time fading. The actual is not just the average, it's the distribution of the fading, the noise floor, interference, traffic distribution, and has a fantastic 3D visualization capability, something that is really impressive. Even I get, I like to play with it, and I will try to demonstrate some things here. And of course, we plan to add new technologies today. As I said, we do LTE, FDD, and we believe that this equipment will be very, very, very important to do inter-cell interference coordination analysis, look how the schedulers are allocating traffic, analyze beamforming issues, and so on. So how did we go about the hardware of this equipment? Well, we are using a very versatile signal analyzing platform that uses the best of a super heterodyne and a direct conversion receiver architectures. So it's a very flexible architecture where we can switch between different receivers, and we are able to provide a very wide 100 megahertz instantaneous bandwidth. The standard units are calibrated. This is a typo here. This is up to 8 gigahertz. Theoretically, we can go up to 20 gigahertz. The dynamic range is in excess of 100 dB. For this, we need to add an LNA that we are building now. And it's a switchable LNA that allows us to have a fantastic dynamic range. And we have very high speed. We use very high speed digitizers and data recording systems. Our spectrum scan rate is 200 gigahertz per second. And it's a very small form factor, very low power consumption. And here is a block diagram of the receiver. I will not go in details here just because of time. Then we have the software, and basically what the software does, it collects and processes the data produced by the CellSpectrum 1000 hardware. This should be 1000, not 2000. We have an unbelievable, powerful multi-screen visualization platform. This is the platform that we are developing for our new product called Cell Designer, and it's something really amazing. It allows us to have multiple views, simultaneous, synchronized. It's fully integrated with Google Maps, Google Earth, including Street View. So inside the tool, you can look at the images of the street, at the towers, and so on. And I will show you in this exercise we are doing today that we had to use it. We did not need to go to Google. We use it from inside the tool. All the views are synchronized in terms of display area. The mouse is synchronized between the multiple views. And we also have synchronization between 2D graphs and geographic maps. An unbelievable display of 3D graphs. We are very, very happy with the results of our development. And we also do a lot of statistical data analysis and display because, you know, having the average that the majority of the tools provide is close to useless. I always give an example in the classes and so on. If you put one hand in freezing water, another one in boiling water, well, in average you probably are okay, but you probably lost both hands. So it's something that average is a very, very dangerous, and a lot of test equipment rely only on average. We give the average and the standard deviation, so you understand how things are spread, what is statistical distribution, and so on. And CellSpectrum 1000 software really provides us several things. It provides us a full-fledged spectrum analyzer. So you don't need to have a very expensive spectrum analyzer that you can only use in the lab. Our spectrum analyzer, you can do drive tests with it. You can capture the spectrum. So it's a really at least a 3-in-1 machine. A technology analyzer, so we can analyze things that no other equipment really allows us today to analyze. Beside this, we had assorted spectrum analyzers, scanners, and radios. We support, third-party spectrum analyzers that we can also use for drive testing, for capturing the spectrum. We support third-party scanners and third-party radios. I wouldn't say that we support all of them, some of them, but this is becoming obsolete because it can be fully replaced by those two first items here. And we can tie everything with our CellPlanner project. So you will see that in the end of the presentation today, we did measurements and we also did predictions from those measurements. We calibrated propagation models and so on. So you will see that it is a very, very complete and detailed. So let's start speaking about the spectrum analysis first. We can have the spectrum analyzer as a standalone device, something that you can have, in the lab, in your office, or even remotely. You can distribute those units remotely along your network, and because they are IP addressable, you see here, oops, you have, you can access them remotely. Here in the lab, I can access the spectrum analyzer from my desk and do measurements, capture things, reprogram, and so on. Another thing is that we can capture live data, store it, or even we can load data that was already stored. So we can analyze, what was happening last week. We had an issue with an interferer. We go there and we replay the spectrum capture. The signal levels can be arranged automatically or defined manually. Spectrum samples can be recorded in a file, basically with a sampling rate of approximately 1 second. So every 1 second you can capture your screen and store it. But you don't just capture the screen. That's what we do for third-party spectrum analyzers. In our case, we capture the screen, but we also capture the spectrum itself. And also we can calculate the power not only in the entire bandwidth, but also when we have the channel that we are looking for. And we show minimum, average, current, and maximum values. Then we can use the spectrum analyzer in a drive or walk test. I forgot to tell is we have a backpack that we can use together with the unit, and it's kind of you don't see really the equipment, so many times we have to do measurements without people noticing that we are doing measurement, like in malls. We don't want to call attention, so basically we just walk with the backpack and we gather the measurements and so on. So in this mode we can define indoor or outdoor measurements. Indoor measurements, we have to point where we are in a map and perform a walk test. In outdoor measurements, we can use GPS, and we can enhance the GPS with a data reckoning system. Of course, we need to configure the GPS. We support several of them. We have to configure the log file. We have to configure the display. We can also configure the base station. So if we want to know what is the distance to the base station and so on, all of this is being displayed dynamically. And the beauty of the software, it allows us to record events. So when we are doing the drive test or the walk test, we can enter some specific events that, oh, we are going into a tunnel now, or we are going into an overpass, or we stop on a traffic light here, or we are behind a building, we are inside an elevator. So all those events, they can be pre-programmed or even typed during the drive test. And here is a capture that while we were doing a drive test and so on. And then this is the screen that we see during the drive test, and this is the log of the drive test that gives us every single capture and tell us, things like what is the time, the lat long, our speed. So we really have an idea of how the drive test was performed, at what speed the captures were done, and so on. A lot of information. And here a little bit about the event recording. Very, very, very powerful. We can see the events graphically after when we play it. So it's something very extremely powerful. We'll talk a little bit more about the events analyzer later on. So we are ready now to go to the second form of the CellSpectrum, is the channel and technology analyzer. And that's something that it's really very, very unique. Well, the spectrum also is very unique. There is nothing really that allows you to capture the spectrum and analyze it at the same time and so on. Well, the channel and technology analyzer, it has 4 stages: the configuration stage, the collection stage, the post-processing stage, and the visualization stage. So we will talk about each one of them. First thing we need to do is equipment configuration. I will not go in details here, it's very extensive. Here are the screen captures of those configurations when we have to configure the hardware. Basically, of course, we have to configure GPS, we have to configure the files, we have to configure the events, we have to configure several things. The IP number, that's another interesting thing, is that we can access also remotely the equipment and gather the data remotely. So it's possible to distribute the CellSpectrum along the network in different places and then gather the data when you need it. Suppose you have something that you detected in a network in a certain place. If you left a CellSpectrum 1000 there, you can capture the spectrum when some interference is happening. So you get an alarm that you are getting some bad issues. We capture the spectrum because this is very, very common. You know? We go to a place, we measure, there is no interference. And then we have a complaint, oh, this site is being interfered. But of course, the interference comes where we are not there. So in this way, as soon as we get an information that the interference started again, we can immediately collect the data. So it's something extremely powerful. Then we have the collection phase. During the drive test, basically what we did here, we did a drive test starting here. Here is our offices here in Western Virginia, and basically we did a loop around, and we came back to the office, and we analyzed, we collected the data. It was about 16 minutes collection. We collected 100 megahertz of spectrum, around 75 megahertz in this area. Basically, during the drive test, the equipment shows the number of PCIs that was successfully decoded. So it tells us, you know, how many cells are we able to see at every single point. And also it gives us a log with all the measurements, speed, and so on. So you can, you know, even hire a taxi to follow a certain route, and you know what speed they were going, and all the information about the collection. Well, then we need to do post-processing. We have 29 parameters today that we selected to be extracted from the 100 megahertz of spectrum. You can extract, you know, from 1 to all of the 29 parameters. You just go here, see what is available, and you move this to the other screen, and then this will be post-processed and so on. Post-processing took about 30 minutes because although there are 29 parameters, there are hundreds of screens and so on that have to be generated, because we capture not just for one antenna, but for all antennas in the network. So it's really something very, very, very extensive. And you can, you know, minimize this if you want. You can capture 1 or 2. Then I find a lot of typos here. I apologize. I have to correct this. And then after post-processing, we do the visualization and analysis, and we use the CellView platform, as I already said. Very, very, very powerful. I will show you some details. It's not the topic of today's presentation, but it's an unbelievable platform to visualize information in maps, in 1D, 2D, 3D, and so on. We use our cell search algorithm that basically detects the cells and the PCIs at its measure point. And then we use cell visualize algorithm that displays the different parameters in 1D, 2D, and 3D. And we have plenty of screens to show it to you. Well, this is a very, very brief showing of CellView. It allows us to have multiple views. Like here, we have top views, we have Google Maps, hybrid map, we can have Google Earth, and we can have Street View, everything at the same time, you know, with multiple views open. And you will see also that all those views are synchronized between themselves. And not only this, they're also synchronized to 2D and 3D graphs. So it's something really extremely, extremely powerful that we are very, very pleased with the outcome. Well, let's speak a little bit about cell search. And cell search, I would like to go in a little bit more of details about how it works, because basically what we will be doing here is we will telling you what your telephone has to do to perform. So we will tell you, what are the steps that needs to be done for you, for your phone to decode, for your device to decode the LTE signal. Everything starts when we look for the 3 possible PSS sequences available on the 62 central LTE subcarriers. And those sequences, they have a very important characteristics. They are Zadov shoe sequences, and each one of those sequences is orthogonal to its shifts. So this allows us really to detect the main sequence and also all of the multipaths of this sequence. And we do this by identifying the largest peaks and decoding the PSS value for each one. Basically is the sequence. So we need to do this 3 times, 1 for each sequence. And we need to do this over a period of a certain number of milliseconds. After we detect the peak, we need to detect it center in time domain. Then we detect the center in frequency domain. So we have to do small adjustments until we find the peak in time domain. Then we do frequency adjustment to find the peak in the frequency domain. And with this first step, we obtain symbol, slot, and subframe synchronization. Exactly the same thing that your phone does. Your device. I cannot speak phones anymore because the devices are, some are only data. Next step is to look for 2 occurrences of the secondary synchronization signal codes. And there are 168 different codes. So we have to look for all of them and see which one we detect for every single PSS that we found. So if you found, 3 PSSs or 3 PSSs repeated 3, 4, 5 times each, we need to go to each one of those locations and try to decode the SSS. When we decode the SSS successfully, and the SS, there are really 2 SSSs spaced of a certain distance, we can detect then what is the cell PCI, what is the cyclic prefix, normal or extended. We can figure out what is the start of the frame, and we can also find ODPCI multipaths. So this is a very, very extensive calculation. Your device does all of this. It doesn't need to do the multipath location that we have to do. Once those 2 steps are done, the next step is to decode the PBCH over the 72 central subcarriers. And basically by decoding it, we are able to find out what is the cell bandwidth, what is the PH-ICH configuration in terms of position and scaling factor. And we also are able to decode the system frame number. And this is also a very tricky thing, because in the MIB we only decode the 8-bit most significant bit, and the 2 least significant bit we need to detect over 4 frames. So in 1 frame we can detect the 8 most significant bits, but then we need a sequence of 4 frames to be able to detect the least significant bits of the system frame. And the reason for this is that because MIB is repeated with the same sequence number for 4 frames. So by finding those 4 equal frames with the same sequence number, we can figure out, where the MIB is, where the 2 less significant bits of the SFM. What is missing now is to figure out what is the number of antennas. So how many transmit antennas do we have? And this in the 3GPP really does it in a very indirect way. We have to look at the 16-bit CRC of the MIB. And this CRC is scrambles with 3 patterns. each pattern gives us a different number of physical antennas. So we have to test the pattern with the scrambling with pattern 1, pattern 2, and pattern 3. And the one that gives us the right result is the one that defines the number of antennas. So it's basically a blind detection to find the number of antennas used. So that's what CellSearch does, and your device also does the same thing, and it's able then to identify the number of PCIs or the cells that are providing signal at every single point. The device that you use, it has to do it once and then it stays in this channel. We have to do it every single point that we are measuring. And we'll talk more about this as we go along. So in this live test that I showed you, CellSearch found 11 PCIs. And those PCIs are listed here. Though this is the number of points that it found for each PCI. All of the PCIs are using normal cyclic prefix. All of them are using 2 antennas. The bandwidth used is 10 megahertz for all of them. The PHCI duration is normal, and the PHCI's resource is scaling factor is 1. So basically, I will not say who is the operator of those sites, but all the sites are programmed in the same way. Once this is captured, we can then start visualizing the data, and that's what we will do next. So our visualization allows us to analyze, to configure. We can visualize the best server, or we can visualize how many servers we have at each point, or we can analyze every single one of the top-end servers, or we can analyze any one of those PCIs that was captured. And also when we analyze the measurements, we can display the power, time, or frequency value of the measurement. So we have the 3 axes, power, time, and frequency. We can display this in regular notation or in the 3GPP notation. 3GPP uses codes to allow us to minimize the size of the information, to reduce the size of the information. So we can, and that's what your device will inform. So that's why we have to show it with this. We can show you the PCI in every single point, the time the measurement was done, and the system frame number. So basically, self-visualize, you see the screen with the PCIs. We choose which one we want, best server or individual and so on. And it allows us, it shows us, gives us a menu of the options we have to choose. So let's speak a little bit about CellSpectrum parameters. Okay, before we proceed, well, not before we proceed. To proceed, I have really to tell you a little bit about how to visualize a 3D spectrum. This is something extremely complex, and also this will give you an insight on how the LTE devices work, because of course to detect the spectrum we have to mimic the way the devices work. So what we call here a 3D matrix, it's a matrix that has the information for every single resource element in frequency, so all the subcarriers, in time, all the symbols, and in power. The power level for every single resource element, and each time we capture you will see 6.1 frames. So, and there is a strong reason to do it. So the first matrix that we capture is this one. This matrix, basically what we capture is, we call it time frequency grid. And time frequency grid stands for a grid with all the resource elements indistinguishably of what they are carrying. So we have 600, this is a typo here, 600 subcarriers and 853 symbols. So it's a very large grid, and but this grid is the way we capture the signal that came from the channel. The received signal is basically no processing. That's how it came. Now we need to synchronize to this signal. So to be able to synchronize, the only way to do it is to analyze the reference signals. So what we do, the next step is to extract from the time frequency grid only the reference signals. So this gives us 100 subcarriers and 243 symbols. And that we call CE raw, channel estimate raw. And basically that's where we extracted all the reference signals. Now we have to adjust, because the clock of the receiver cannot be the same of the clock of the transmitter. They are they don't have exactly the same frequency, and for sure the phase is not aligned with the received signal. So we need to do those adjustments. So the first adjustment we do is to adjust our time offset drift, because what happens, even if we adjust the start of a frame, because the clocks are different, along the frame we start drifting, and after the middle of the frame you already will start getting errors because the clocks are not aligned. So we have to do an offset drift estimate and adjust this for every single frame, trying to adjust both clocks. Then we need to start also, when does the phase starts for the frame. This is very, very important, because remember, we are sending sine and cosine. If we are a little bit out of phase, they are not sine and cosine anymore. So we have to, and this is what we call CE talk, is the second part. Then we do a frequency offset compensation. And finally, then we have an adjusted channel estimation. So now we know how the channel is behaving at that moment, at that location. What we do then is that for each one of those, we generate a time frequency grid. And those time frequency grid, basically, they have, they are intermediate results, but they may be used during the extraction of the 2D and 3D parameters, 1D parameters. So we need them as intermediate steps. But the channel estimate is still a little bit prejudiced, because we had fadings, and some of the resource elements that carry the reference signals may be still subject to large fading. So what we do a smoothing of the channel estimate by interpolating between adjacent reference signals, and that smooths a little bit the fading. And finally, we have the channel estimate based on the smoothed channel estimate, and only then we can really do the RX grid. The RX grid basically is a corrected TFG with all 600 and 853, 600 subcarriers and 853 symbols. So it's 6.1 frames adjusted, corrected for the channel distortion and so on. And that's what is our RX grid. We also need to do some another interpolation that we need to estimate based on CS smooth. We need to estimate another grid, and this grid we will be using to calculate the fading in time and frequency. And basically we will use the TFG also and the CS smooth to derive the 1D parameters like RSRP, RSSI, and RSRQ. So you can see that it's a very complex process, and we had to dominate every single step here and do it in an optimal way so we can really extract properly the parameters. We are probably doing it with much more care that you can do in a device, because of course we have more powerful processors and so on available to us. Here is a description of the different 3D matrices that we already spoke. And finally, we will go to 3D parameters. So we will start getting now some results, extracting some parameters. Well, remember the TFG grid. What we are doing here is that we are showing you one capture in a line of sight. The sight is here. So we have a line of sight and another capture here where there is no line of sight. So just to exemplify, of course, because we have a very short window, and here we have the legend with the different power levels that we are applied to the next screen. This is the screen of the TFG, and I would like to describe this screen to you. Basically, here on the right-hand side, we have what we call a bird's view. This bird's view shows us always the complete capture of the total number of subcarriers by the total number of symbols. And this is represented here. Okay, and the power level range is represented here. Here we have several configurations that we can do. In the middle, we have a screen that we can zoom in part of this bird's view. And then we can zoom in more and more and more. And here we have the 3D view of whatever is in the middle screen. And you will see, I will go live and I will show you, I will manipulate this. Beside this, we can cut this view in different locations in terms of subcarriers. We can cut it on any subcarrier or any symbol, and this then will be shown in the graphs here below. So we can then understand what is happening. What I will do is just to show how powerful this interface is, and I will not really show you half of the features. I just switched to the actual tool. Here we have a view, and we are showing which point are we looking into. The configuration of this screen can be done very easily just by pressing one button. It will center the information. So suppose I zoom in. And then what we are capturing here, we are capturing here also on this bird's view, and here on the, so we can see where we are. And here is my 3D view that I can rotate and look on different positions. I can do a side view, another side view, a top view, or a default view. And I can even rotate and so on. And then I can do things like this. I can zoom in here. And everything zoom in. And you can see that the graphs also zoom as we zoom here. So if I go just here where the MIB is, and then I have the information here. So it's an extremely powerful visual interface. And here also you can see that I can look and I get the information about every single point here also. And not only this, we can also see the statistics here of the tool for the power and so on. And everything is synchronized. So I will go back to the presentation and we can go to the next screen. I really don't have time here to show all the features, you know, just maybe one of the features that is very interesting is that everything here is dockable. So I can remove this or I can put it back. I can do a lot of, you know, I can dimension, change the sizes of whatever I want. I went back to the presentation. Okay, we are running out of time, so I have to go faster. So this is the line of sight signal. Now I will show you the non-line of sight signal. So if we look at the line of sight signal, the average power is about 60 dBm. When we go to the non-line signal, the average power now is 79, 80 dBm. Okay, and you can see the distributions and so on. Well, this is the raw signal. It was not corrected. So what we are doing next, we are extracting only the reference signal that are known signals. So now we have the variation here of the reference signals that are not corrected yet. And you can see clearly that it varies on time, but the variations on time, although there are some fast fadings, there is a slow fading that takes several frames, because remember here we are only representing the reference signal, so this is a distance of 6.1 frames. So it takes several frames to fade in time, but in frequency it really fades every, I would say, 3, 4, 5 subcarriers. You know, you have large fadings and so on. So this is a very, very important information for us to design our system. So what happens with non-line of sight? Well, in non-line of sight, the fadings are even much pronounced, more pronounced, and here, but in time they are still following more or less the same pattern, but in frequency they are much more severe. Then we go to CS smooth. I'm not presenting here all the captures because it's a lot of captures. Again, the line of sight signal, this is the color table. And CS smooth, we make it smoother because we, of course, we are filtering, and you can see it here. We removed a lot of the fast fading, but the slow fading is still there, because this one is the one that we want to correct. Okay, is the slow fading. And here is for a point that is non-line of sight. And you can see here that the variations are much more pronounced. This is the overall grid already corrected by the channel estimation for a line of sight signal. So now here we have the corrected grid for antenna 0 and for antenna 1. And you can see that there are differences between both antennas. So we cannot assume that both antennas, and this amount of difference is the one that really will allow us to use MIMO or not. So we have to develop the special analysis just to do this, to be able to analyze where we can use MIMO, where not. And this is for non-line of sight. You can see that it's much more noisy, and also the antennas are not exactly the same. Finally, we have the receive grid that has all the points. So in the receive grid here, we have the 600 subcarriers, the 854 symbols. We have a 2D view at 300 subcarrier and symbol 0. And basically what you have here is that we have a lot of like fadings here. And I would like to ask you a question. Why do we have suddenly so much fading? Well, this is not really fadings. These are points, subcarriers or symbols that are not being used. So there is no information sent. So what we read there is basically the noise flow. So there isn't really the information. Basically, I would say it's held in this area here, and the rest is that a lot of those resource elements are not being carried and so on. And that's a non-line of sight now, RX grid. Also we have a similar behavior, and here clearly we can see where the PSS is, where the MIBs are, and so on. In the next release, we are placing a map on top of this view with the location of the main elements of the frame. So we will show you all the subframes, all the PSSs, all the MIBs, and so on. So it will be easier to identify the elements. And also we can see in red where traffic is being allocated. No, so it is not everywhere. So I think we can have a break here. Roy, is there any questions before we go into 2D parameters?
Yes, Len, we have a few questions, so I will take a few in the interest of time here. The first one, storing spectrum is a great idea, but does it not require a lot of storage space?
Yes, it does require a lot of storage space. So what we suggest is that you use hard drives. They are very inexpensive. So you use a 1 terabyte hard drive to store the spectrum, and we have a policy that the spectrum is stored for a certain number of days, and then it is deleted, or it is marked not to be deleted. But it requires a certain discipline in terms of providing where to store and so on. But the capability it gives you are so powerful that it is worthwhile. Just to have an idea, I don't recall what is the amount that we stored here, but it was some megabytes. It was not even gigabytes.
Okay, I'm going to take a few others. Can CellPlan develop custom reports based on the data collected?
Yes, we are talking to different several operators, and we are discussing their needs. And our idea is to keep enriching the reports because this tool provides you so much information. So what we are doing now is to developing processes that will extract the information that each operator requires.
Okay, I'm going to take 3 more here out of the loop. There are a number of questions, so if we don't get to your question, folks, so we will certainly answer via email Apologize. Can CellSpectrum be used in the uplink?
Very, very, very interesting question. We have debating this, and it's something that we plan to do. And the main reason for this is that there is no visualization of any sort today in the uplink. So what we plan to do is to develop a module that can be placed, can tap into the antenna of the base station, tap on the receive side, and display then the same displays we have here, 3D displays. It can be displayed also.
Okay.
So it's something for the near future.
Okay. Can CellSpectrum interface with other tools?
It cut, Roy.
Sorry. Can CellSpectrum interface with other tools?
Yes, it can interface with other tools. We export data in several formats. If you need a special format, we can work with you and develop a special format, or we can open our format and other tools can read from our format.
Okay, I'm going to take the last one, then we'll move on in the interest of time here. Can the captured spectrum be used as evidence to show irregular transmissions?
Yes, that's a bit of it. So, you know, one of the issues that we find a lot, people request us to find who is interfering with the network, and the interference is not constant like we had. Suppose in some island we had people bringing phones from the US, and those phones were interfering in the band, wireless phones, not cellular, but regular wireless phones, home phones. And of course it was only interfering when the phone was being used. So we had a large difficulty of pinpointing, you know, and interference was coming from everywhere. So each time we go there to measure, there is no interference. And with this way, we can, you know, as soon as the interference arrives, we can capture it remotely and capture the spectrum and then use this as an evidence. Any more? No.
No, I think we can move on. There are others, but in the interest of time, we need to move on.
Okay. Well, let's speak about a little bit about 2D parameters. So the 2D parameters, they are extracted from the 3D matrices. And one of the most important ones is the PSS-PDP, Primary Synchronization Signal Power Distribution Profile. So this profile allows us, as I said already, because the PS sequences are orthogonal to its shifts, we can detect all the occurrences of the PSS sequence. So with this, we can detect all the multipaths. And for OFDM, for LTE, this is essential to define the cyclic prefix. We did several measurements, and we saw that in many cases, people are still using the normal cyclic prefixes, and they should be using extended cyclic prefix. Cyclic prefixes can be defined by cell, so there is no issue. It doesn't need to be uniform over the network. And but there was no way to figure it out before. So we did several measurements, and we are finding that in some cases the cyclic prefixes are very, very important. So here we show for the line of sight point, we show the all the different multipaths. Of course, everything below here is noise, but we have some multipaths here. Those ones are probably coming from cells, distant cells with the same PCI based on the time. But then we did a zoom here, and that's what we got. So we got one, another one here, another one here. So we can specify a window, and we then can calculate how many multipaths we have and what is the distance between the multipath and the signal. So this is the line of sight signal, and this is the non-line of sight signal. And you can see that we have some multipaths that are 15 to 20 microseconds away. They are basically 10, 12, 13 dBs below. So probably this will recommend an extended cyclic prefix. But what we need to analyze is what is the extent of the area that this happens, because of course if it happens in one point is one thing, if it happens in the whole area, only then we need to change the cell. Another 2D parameter is antenna correlation. I will not go into mathematics here because of time, but basically we define here variance of a variable, of a spread of data. So how does the data vary between itself? And then covariance is how two sets of data of change between themselves. So covariance is a very, very important indication of antenna correlation. And the Pearson product moment coefficient is based on covariance. And basically what we do, we generate a variance and covariance matrix. And this is the matrix that we generate to calculate, and we show then the covariance parameter to analyze how much antenna correlation we have to verify we can use MIMO or not. Is it worthwhile to install, 2, 4, 8 antennas? This is the drag test for covariance, and this is the 2D graph. So anything above 0.5, no MIMO. Anything below 0.5, you will have a MIMO possibility. So I would say that in this drive test, this is the area that has MIMO possibility. But this is expressed on sample number. So unfortunately, this area is an area that there was a traffic light, and we had many sample numbers. Because those graphs, they are synchronized with the 3D view, what we found that the area was here. So this is in this whole area that this cell is providing on this side, and the cell is here. This is the only area that would be suitable for MIMO. So that's something that was is very, very powerful. But we will have a whole seminar about MIMO next month, so I will not go much further. This is the matrix. That's the average. So you can see that the average is 0.733. It's very high. That's the standard deviation, and so on. Then we will talk now about 1D parameters, and that's basically the same parameters that other tools provide. They don't provide the 2D and 3D, but they do provide the 1D parameters. But I believe that we are providing them with a different flavor and with much more information. The first parameter, we already discussed this in our measurements webinar, is RSRP. And is basically what is used today to characterize the signal power, because it's a known transmitted power. So all the other elements, resource elements, they can not be transmitted at all. So if you need a reference for power, the RSRP is very, very important. One thing is that very important to note is that the RSRP is average per resource element. So it only measures reference signals, and it indicates the power for one resource element. 3GPP provides a table that maps RSRP to values. So we can either represent the RSRP in dBm, or we can represent it in 3GPP values. Here I show the calculation of the maximum value that you can measure and the minimum value you can measure. Even so, for a device, 3GPP specifies that the accuracy is plus or minus 8 dBs. So this is not a very great accuracy, but it's understandable that a device has, its limitations is not a test equipment. So that's why doing measurements using phones, it's very, very questionable. So we strongly recommend that you use professional equipment to do those measurements. And the question is, what is used for? Well, it's a strong indication of the receiver signal strength, mainly because in the RRSP we do some interference filtering because we know what is the pattern that we receive over the set of reference signals, and this is filtered, and by filtering this we remove a large part of the interference. So RSRP is a very good indication of the received signal strength. Now, what it can be used for? Well, it can be used to calibrate the propagation model, analyze the precision of the signal coverage predictions, locate areas with low received signal strength, and analyze the best server and its transition along the route. I will show you some example of those applications still today. Well, although this is one single parameter, we have here 10 ways of presenting information about it. So the first screen is the one that shows the parameter in dBm. The second shows the parameter in 3GPP value. The third set shows the PCI of the best server. The fourth, the SFN number. The first, when it was the time when it was measured. The sixth, the number of servers. The seventh shows the first server at each point. The eighth shows the second server at each point. And the ninth shows the third server at each point. And the 10th set shows really only for a single PCI, not a best server. So this is the best server signal level along the route. So we started here, we drove here, and then, so this is the direction we drove. And this is how the signal behaved along the route. Here we use 3GPP units, is the same value but now translated to 3GPP units. This is a very important way of looking at it. Basically what we are showing here is the best server PCI. So I will ask you a question. What does this area suggest? This area and this area. Well, mainly this area suggests that we don't have a dominant best server. So most probably in this area we'll have a lot of issues. So let's see if I can show you this in the tool very quickly. Let me see, I go here, I say, look, I want to look at the RSRP, and I say visualize, and I click here, and I bring this screen here. I will enlarge the screen. So I have here the screen, and now I can drive test, and you can see that I am moving along the drive test route, so I can analyze. So I want to see the PCI. So now I can see the PCI here. I am moving along the route, and suddenly I arrive in the problem area. So the problem area starts here. I hope you can see it in the yeah. And you move here along, and you can see that there is a lot of issues here. And then you go back to a normal status. So basically in this area, something needs to be done, or another site, or adjustments, and so on. And then we have another area here that we also have changes on the best server. So this is a very, very powerful graph. And you can see that just because we are displaying it and we have everything synchronized, it's very easy to analyze and look into it. So let me go back to the best server. So next is the best server SFN. Then the measured time, so you can find when the measurement was done at which location. The number of servers, and you can see that in some places we have many servers. The first server signal level, the first server PCI. So it's really the first server that is having a lot of problems. This is the second server signal level and the second server PCI. So you are really in problems here because you have issues with the second server and you have issues with the first server. So it doesn't matter what you do, you have a lot of issues. And then the third server is clean, but of course it is the third server. And the third server appears exactly on this area here. Now we have only for one PCI, so only for this site here, and you can analyze side by side, and then you can take actions. The next measurement is a measurement that you are probably familiar, is the Received Signal Strength Indicator, RSSI. But for an OFDM system, this measurement takes a totally different connotation. And it's much more complex because not all subcarriers are transmitting all the time. The transmission depends on traffic, and that changes the power level transmitted. So we need to understand first how in LTE the power level is adjusted. First, that the OFDM signal is really combined into a single temporal signal. And that the transmit power is adjusted to define a predefined power level for the reference signals. And this predefined level is called energy per resource element for the reference signal. And this is a value that it is broadcasted in CB2. So the devices, they read this value and they know what was the energy transmitted for each resource element. In addition, there is another parameter that is transmitted in CB2 that is the power boost. And the power boost gives the ratio between the PDSCH and the CRS. The power boost varies between 0 and 3 dB. So once you assign the power to the reference signals, you assign the power boost, you can calculate the power for every single of the other resource elements. But this power can be used or not, depending on traffic. So RSSI is a measurement of the total power received, and that is how it is specified by 3GPP. And of course, the power amplifier has to accommodate all the subcarriers, so it has to use this rule of the EPRE and so on. In the table below, we calculate the EPRE for different bandwidth, assuming 10 watt, 10 megahertz, and a power boost of 0 dB. So you can see that the EPRE here is always 12 dBm. Of course, the EPRE gives us the average power of the power amplifier, but due to PAP, we need to accommodate the peaks. So generally, a margin of about 10 dB is required on top of the power capacity of the power amplifier. So what is the issue then with the RSSI? Is that the RSSI will vary with traffic. So depending on the traffic, you will see that there is a different value of RSSI. So it's a measurement that is really very critical, because if there is traffic, there is one measurement. If there is no traffic, the measurement is different. And for a two-antenna system, the variation can be up to, from one antenna system can be up to 10 dBs, and for two antenna systems up to 8 dBs. So 3GPP specifies a wideband measurement. So it specifies, well, it should be measured across the whole band and then expressed in terms of one resource block. Also, excuse me, for the whole band, not of all resource blocks. Well, what we decided to do is to do two other measurements which are independent of traffic. One is measured only on areas containing RS. You will say, well, then this is RSRP. Well, it's not, because RSRP is filtered with the RS pattern. When we measure RSSI on the RSs, we don't filter. So it has a component of noise and interference. And the other measurement is done on the MIB area, because the MIB also always uses QPSK modulation, so everything is uniform. So this here, we show the RSSI wideband, and we show it along the route. And the average here is minus, I believe, 40 dBm, yes. And we have a standard deviation of 8. Now, if we measure this same RSSI only on the CRSs, the average now is minus 46. And if we measure this on the MIB, the average is minus 48. We need to normalize these figures, because each one is measured over a different kind of bandwidth. So you will see that we have to normalize this. Maybe one idea would be to put the normalization in each measurement, so something to be analyzed. Well, another 3GPP measurement that we discussed also in our measurement webinar is RSRQ. And RSRQ is very important because it is used to adjust the modulation scheme and so on. Well, it happens that RSRQ, according to the 3GPP formula, depends on RSRP, that's fine, but also depends on RSSI. And here we calculate the maximum value of RSRQ, that is minus 3 dB, and this happens when no traffic exists at all. And the minimum value of RSRQ is that when we have a lot of interference, we have a signal-to-noise ratio of minus 9 dBs, and then the value of RSRQ is minus 20 dB. So 3GPP specifies an accuracy of 3.5 dBs and plus or minus, so it has 7 dB excursion here, and so on. But that's mainly because there is a big variation due to RSSI. And also the 3GPP has here a table that maps the values of RSRQ to integer values, so it uses less bits to send information. So here we show the RSRQ wideband, and here we show it in, so here is good, here is good, here is bad, here is more or less, so-so. Now we show it using the 3GPP numbers. And now we show it using the CRS. So we remove the traffic issue. Again, good, bad, so-so. And here we show using MIP, and also we have similar, but the bads, you know, are not appearing here. So bad. There we have good and we have so-so, but we don't have really bads. So, and that's because of the traffic influence, so we need to analyze this very carefully when you do the analysis, because the RSRQ measurement is always compromised by traffic. So here we did a table comparing RSRP, RSSI, and RSQ. Remember that we have to normalize those measurements. So here we have RSRP and RSSI, and the measured values, the standard deviation, the 3GPP value, and over how many subcarriers it is measured. And then we did the energy per resource element in average. So you can see that the RSRP is minus 68.1. But the RSSI CRS is minus 66.9, so it is a stronger value because most probably the CRS has a power boost, and the MIP value is minus 67.5. That is higher than the RSRP because it includes the interference. So, and here also it includes the interference and the power burst, and here it includes interference. So, and here it includes traffic. So, because some traffic channels are not there, it's giving a lower value than the actual RSRP value. So this is a very, very important analysis to be done. Then we go now to analyze the PSS power. So another way of measuring the power is to measure the power of the PSS 62 symbols, because this is also always transmitted, always constant, but it is subject to interference. But because we are extracting the signal, well, we have here an average of minus 54. Then we can also measure the total signal power, and the signal power is measured over reference signals averaged by their neighbors, so it's measured over CS smooth, and the measurement is done for each antenna. And here you can see that the signal power is very similar for both antennas because they are transmitting the same thing. The noise power also calculated for each antenna. And then a very important graph, a frequency fade. So we are showing the fade, the average value. This is the fade in frequency. So it's 137 hertz. And here is another fade. And you can see that the fade from antenna 0 is different from the fade of antenna 1. And that's what will give us some MIMO capabilities. Then we analyze the time fade, same thing. You can see that there was a time fade here. And so Spectrum allows us to analyze all the 1D parameters in one single table. So this is very, very powerful, and also you can switch between them very, very quickly. And here we did a summary of the 1D parameters. What is the average value, so you can compare and understand what is happening between the different antennas and so on and so on. Well, this finishes the measurement part, so let's do some practical applications. And one of the practical applications that we did was calibration of the propagation model. We took a relatively poor database. Topography database was the USGS database with 30-meter resolution. Here are the measurements on top of this database. The morphology database was really not very good. 30-meter resolution also, and here's our area. So we didn't use very good databases. We certainly may get better results with better databases. This is the map image over the measured area we measured. This is the site that had the PCI that had the most measured points. This is the measurements over the Google Earth image. And we used the propagation model Korovaichuk 3D. We actually tested it with the different propagation models. The 3D, Korovaichuk 3D is the one that gave the best result, although the database is not as good. So better database will get much better results. Here are the parameters that we calculated for this terrain. Of course, if we have a better terrain, we'll have much better results because the Korovaichuk 3D model is highly influenced by the quality of the database. But even so, with this poor database was the model that gave the best results from the models we tested. Here we calculate that the average deviation and the standard deviation for the measurements. So we predicted every single measurement point, and the average deviation was 0 dB, and the standard deviation was 6.16. With a better database, we probably will get less than 5 dB of standard deviation. And that's, remember, we only used 230 points, something like this. So it's really a very, very good result. This is in blue, we have our prediction, and in red, we have the measurements. This is by sample number, and this is by distance. And you can see clearly here the slope, and you can see that both are very, very, very close. So after we calibrated what we used was the parameter we used was RSRP. After calibrating, we did a prediction then. Well, we wanted to predict the cell for PCI 428. We didn't know the site characteristics. So we went into our tool and opened Street View, and we looked at the tower, we looked at the height, gave an estimate of the location of the antenna height. We estimated the antenna azimuth. We used antenna gain and pattern and transmit power we assumed. Basically, we used the typical values that we use in our own design. And we use the calibration used with K3D. Of course, all those parameters, we have to have them for the calibration also. And now we show the overlaid measurements over the prediction. And well, you nearly cannot see the measurements because they coincide with the prediction. So there is a small difference here, but you can see that the measurement disappeared because the prediction and the measurement are very, very, very similar results. But we also did something else. We generated predictions from measurements. So without any prediction tool, we took the measurements. Well, we used our prediction tool. We used this site, again, measurements. Actually, no, we did this for the best server. So we applied the best server, and we said, well, what will be what happens here in the middle, what happens here, what happens here, what happens here, and here. So what we did those are the measurements extracted, and then we did an interpolation, what we call a 3D interpolated measurement. And here you have the RSRP. And you can see that the measurements and the interpolation, they match unbelievably well. So we are very, very pleased with those results, very powerful results. And, you know, we didn't have much information at all, just the position of the site. And with this, we were able to interpolate the measurements. Here is the interpolation now shown. And you can see starts here, green, ends here, red, a small green area, here, here, here. So it's really does predict very, very well. And it's a very complex 3D interpolation. It was a thesis of one of our top researchers here, and it does really work very, very well. And here, without the measurements showing that. But the question is, well, you have a lot of red here. Do you have a better resolution? Yes. This is the actual resolution, and here you can see that we are moving very, very little the colors, and you can see how things fade and so on and so on. So it's this shows the 3D interpolation granularity. Okay, let's make a very brief summary. So the broadband channel is very complex and requires extensive analysis. An LTE network requires an in-depth understanding of the RF channel behavior and how it can to be properly configured. So multipath spread, time fading, frequency fading, antenna correlation, interference, noise rise, and many other parameters in LTE require this knowledge here that it's very, very important. Also, significant CAPEX and OPEX savings can be obtained by understanding the channel behavior. Suppose we want to deploy multiple antennas, does it make sense? And also it reduces chasing its own tail by understanding the cause of the issues and not relying just on the symptoms. With this, we finish the presentation. We will speak about new products, but before, let's see if we have questions.
Yes, Leonard, we have a number of questions, so I will try to see how many we can get to. One, can we request the extraction of additional parameters?
Yes, as we said before, we can extract special parameters. We are actually talking to operators. We are visiting some operators next week to do some MIMO analysis and so on. And of course, during those interactions, we will come with additional parameters to be measured, or the way to present the parameters, you know, should we do EPRE and so on and so on. That's the beauty of having, you know, develop the tool and having the tool with us connected to the planning tool. So, and we have all those capabilities, so that's not an issue.
Okay, the other question, a couple more. Are you planning to develop a interface for LTE TDD?
Yes, not only for LTE TDD, but we are planning to develop it for UMTS and for GSM, WiMAX, and Wi-Fi. That's the big advantage of having a software-defined receiver. So we are really technology independent. It's just a question of putting effort into it. The reason that we focus on LTE FDD is that because there are several networks that we are designing and deploying, helping to deploy, and we had urgency in this kind of information to properly design the networks. But of course, we also have people with LTE TDD, mainly in the Asia-Pacific region. And then we have, of course, Wi-Fi and WiMAX. So that will be our next step. And then we'll go into EMTS that also has a broadband channel. And just to complete, we will develop GSM. But this will be done probably over the next year.
Okay, the cell view interface looks very powerful. Is it available with the regular cell plan tools?
It cut, Roy. I missed.
The cell view interface?
Can you repeat, please?
The cell view interface looks
Yes.
very powerful. Is it also available with the regular cell plan tools?
Yes, actually it is the interface that we are developing for, well, we are already using it in Cell Planner, in Cell View family, Cell 2, Cell Optima, but it's being consolidated inside Cell Designer that we will speak about now. It's unbelievable viewing tool. Something I would say the fifth generation, a new generation of tools.
Okay, we have several other questions, Leonard, but we are already running over our time allocated for the webinar. So why don't you proceed to the next section, and then we will get to the remaining questions. We will answer them via email.
Okay, well, Cellplan new products, I will speak very, very briefly. I don't want this to become marketing. We already spoke enough about CellSpectrum, so let's speak about Cell Designer. That is the tool that we are developing now. It consolidates all our other tools, all the experience of 20 years. This new generation of planning tools, and is a collaborative work with operators, and we value your input. So if you want to be part of the team, please contact us. Cell Designer is, as I said, a new generation of planning and optimization tools. It has qualities that are very, very unique. It will help you to document the physical deployments, document the network parameters for each technology. The mood technology, of course, too. Very flexible data modeling according to what we said in the webinar. The traffic can be allocated to different technology, fractional resource planning, performance evaluation, and has an integrated backhaul. Supports all the technologies simultaneously. Very, very powerful. It does a full network representation, so it's not just representing cells, it represents sites, tower, antenna housing, antenna systems, very advanced antenna systems, fully network parameter integration, and KPI integration. Of course, has the most advanced propagation models. You will get even a more advanced Korovaichuk 3D model coming. Has multi-technology dynamic traffic simulation, automatic resource planning, automatic cell planning, and thus performance prediction. So it's really a unbelievable tool. As you saw, Google Earth integration. It provides a network master plan that can be used for SON and IC. Has integration of field measurement data and integration of KPIs. Well, JS database editor, backhaul planning, also very, very powerful. Everything in one single tool. Here you can see we are modeling thousands of backhauls in the city of Sao Paulo, all in 3D over Google Earth, and you can rotate, you can do unbelievable things. So with this, I terminate my part of the webinar, and I'm really pleased with today's webinar. I hope you are also. So Roy, I pass the presentation to you.
Okay, Leonard, thank you very much for an excellent presentation. I'd like to also thank all the attendees for attending today's webinar. As Leonard pointed out in the beginning, if you missed any of the previous webinars, you can certainly find these on our website at www.cellplan.com. The recorded session of this presentation and the slide deck will be posted online on our website later on today. You can also go there and find the recorded sessions of previous webinars and the slide decks for those as well. Our next webinar will be on November 5th. We look forward to having you on board with us at that time as well. Thank you once again and have a pleasant day. Thank you.